meeting, so it's like a nice get-together to learn about biochar. As Steve said, I'm from University of Illinois at Chicago. I'm in Department of Civil and Materials Engineering. In my lab, we do research on environmental remediation engineering. So basically, how do we control environmental pollution? How do you remediate environmental pollution? So that's kind of a broad area of research that we have in our lab. We have different types of projects in relation to biochar. We have project dealing with using biochar as a soil amendment in phytoremediation. We have a project that deals with use of biochar as an amendment for landfill cover. Erin, my student, she is having a poster here. You can look at that research. And we have a project where we use biochar to remove nutrients from wastewaters and use nutrient-laden biochar for agricultural purposes. And this other project that I'm talking about today is using biochar as a filter media to remediate polluted urban stormwater runoff. So this is my presentation. So this picture, you can see it. This is a beach site in Chicago. If you go along the Lake Michigan, Lakeshore Drive, along the Lake Michigan, we have city of Chicago has several beaches. This is one of the beaches on south side. It's called Rainbow Beach. And whenever it rains, you can see that all the stormwater runoff. This is an adjacent parking lot. This is the Lake Michigan. This is the beach. And whenever it rains, all the surface water runoff is, not only from this parking lot, but from the adjacent areas, that runs off and gets into the lake. So this stormwater is a non-point source of water pollution, which is really difficult to handle as compared to point sources. So this project, I'll show you, funded by US EPA Great Lakes Program. They are interested in protecting the beaches. And based on the recent data, number of beach closing days are increasing, and that's mainly due to the pollution. So they monitor, of course, E. coli concentrations, and whenever the concentrations exceed certain threshold, they close the beaches. So we have been finding, number of beach closing days increasing. That means, pollution events are happening more. And we did some evaluation of stormwater events versus, these pollution events or beach closing days. There is some correlation, not a definitive correlation, but there is some correlation indicating that, the pollution source could be this stormwater runoff. What kind of contaminants you are dealing with? Especially in the urban environment, we are dealing with nutrients. Lakeshore Drive is right there. We apply a lot of salt during the winters, heavy metals, PAHs, and of course E. coli. So you can see here in this parking lot that I was showing here, there are a lot of these birds, and obviously that's the main source of biological contamination. So we have not just one type of contamination, we have mixed contaminants, and how do we remediate this problem? And again, this problem is because we had old infrastructure, sewage and stormwater, which is not properly designed, and in some cases we don't have any engineered stormwater systems. So basically, currently, all the stormwater is directly discharged into the lakes through these beaches and causing all these issues. So how do we address this problem? There are several best management practices to address urban stormwater that include these detention ponds, bioretention, infiltration basins, permeable pavements, all kinds of things. For example, detention ponds, basically, you have a big pond and you accumulate all the stormwater runoff, and that way you can address a lot of these stormwater issues. That is commonly done in suburban environment. But in urban environment, for example, just by Chicago area, you don't have a room to build those detention ponds. So a lot of these things are economically unfavorable in urban settings. and technically not too complicated, but not well established in terms of how they work and how reliable those are. As I said, they are not feasible in urban environment because of the constraints on the real estate, and also a lot of these systems don't address the multiple contaminants that I'm talking about that is coming in this urban stormwater. So the only alternative is to use filtration systems, and to remove the particulate matter as well as dissolved contaminants that are coming in urban stormwater. So basically, you have a filtration system, but you need to have a filter material that can actually remove the contamination. So there are a lot of different types of filtration systems and using different filter materials. So these are the different types of filter materials that have been used in filtration system. So my research is, why not biochar? Biochar, if you just based on the characteristics, it has excellent potential to serve as a filter material. Why can't we use this one as a filter medium? So our research is to evaluate biochar's potential to remove different contaminants that are present in stormwater, and quantify contaminant attenuation or degradation capacity, and also hydraulic efficiency. It's a lot of times we are dealing with stormwater events. Suddenly you have high flow event for a short period of time and there's no flow afterwards. So it has to be hydraulically efficient. So you have to have really high permeability. At the same time, you should have a good reactive or adsorption or degradation characteristics to remove the contamination. So that's kind of you have to balance contamination removal as well as hydraulic efficiency. Our ultimate goal is to kind of develop an in-ground permeable reactive filter system. So idea is, the water, instead of directly discharging into the lake, why don't we divert that water through these filter systems, have the contamination removed, and then discharge into the lake. So that's concept of in situ permeable reactive filter system. So just below the ground, putting it in the system and then have the water diverted through that system rather than directly discharging. So just to give you an idea about what this system is like, it is all about below the ground. It is, let's say, it's the ground surface. So you let the stormwater enter into this system. So this is the inlet well. So it comes in here, and you have a pipe that comes up here. It's the perforated. That water comes in through here, and it passes through this filter media, and this is where all the contamination removal happens. And let me use this so that both sides can see. So the cleaned up water can come out and then get discharged. Of course, if you have a heavy storm event, which this filter system cannot handle, you have an overflow system that, of course, could be rare, but you don't want the filter to be damaged, so you have an overflow system like that. So this is kind of a system. It's a below ground, and putting this one and trying to solve this urban stormwater problem. So in our research, we wanted to see whether we can use the biochar as a filter medium. So first, what we wanted to do is we wanted to do some lab experiments, find out what is the potential for its use. And to do the lab experiments, we wanted to know what is the typical stormwater quality that you can expect. So we did a comprehensive literature review to find out what kind of contaminants that you will find in urban stormwater runoff. So this is the literature. This shows all these different types of contaminants. What are the range of concentrations that are found? And this is the reference. And also, I have listed here, there are two standards: National Recommended Water Quality Criteria and also Lake Michigan Basin Water Quality Standards. So you can see these are kind of acceptable limits of the contamination that contaminants that are found. So this is only part of the table. Here is the contaminants keep on going right here. So basically, we did a literature review, and then after, based on all these things, we wanted to create a synthetic stormwater. So basically, the synthetic stormwater that we created had nutrients, metals, PAHs, and E. coli. So basically representing the concentrations that we selected, represent the worst case scenarios. Okay, so these are the concentrations that are found typically based on the literature review. And what we did is we created synthetic stormwater, within the range of these concentrations. So basically they're all mixed together. So you have a mixed contaminants in this, synthetic stormwater. So the biochar, what kind of biochar did we use? We characterized, I think, 8 or 9 different biochars in our lab. And we chose this particular biochar for this research. This is the biochar created by Chip Energy. We found out that, the biochar that is created by Chip Energy has been consistent. We got 3-4 times in terms of the characteristics. That has been a big issue. If a particular biochar can have consistent characteristics. So we found out that this biochar provided by Paul is very consistent, and we also did some environmental testing to look at concentrations of PAHs and those kind of things in those. So this biochar provided by Chip Energy didn't have any PAHs in them compared to other biochars we tested. So we thought this is the biochar best suits for this kind of application. So initial characterization of this biochar, we did both unwashed and washed. Here are the properties of those. So you can see this, and then we did column experiments. So basically we have a large plexiglass column, and at the bottom we filled with pea gravel, and then we had a biochar, and then we have a pea gravel at the top. And then basically we introduce, initially we introduced water, just a regular water, deionized water, and collect the sample just to look at, if there are any contaminants leaching out of biochar that we put in. Just is there anything, that is leaching out. So we do that one. After that, we put a synthetic stormwater in this one. We flush through it, at least 3 pore volumes. After each pore volume, we collect the sample. So we get those samples. And then at the end, again, we flush with water to look at, the contaminants that are probably absorbed, get desorbed easily. So we have that last water flush situation also. So that's the procedure, and we got all these samples at the different time periods, and we did the analysis using the standard methods, ASTM, USCPA methods for pH, electrical conductivity, oxidation reduction potential, total dissolved solids, nitrogen and phosphorus, heavy metal concentrations, and PAHs, and also E. coli. Obviously, you're going to have this presentation, so you can see all these procedures, later on if you want. But these are all the standard procedures that we followed. So what are the results look like? So here are the results. I want to explain one graph so that you can follow all the other graphs. So this first one, you see these three graphs here. Those are for unwashed biochar. Basically, initially, this is the synthetic stormwater. This is stormwater. This is the initial flushing, and this is after the flushing of the synthetic stormwater. This is showing the pH. So synthetic stormwater had this pH, and when we flushed just the deionized water through this material that had that pH, after flushing this synthetic stormwater through this material, we had this pH. So there is not significant change in the pH. And then these are for washed biochar. So you'll see this one. The first one is a synthetic stormwater, and the second one is just a washing with the water. And these next three are after each pore volume of synthetic stormwater flushing, and the last one is a final wash with water. So I wanted to put all the results together, but that's why it makes it a little bit complicated. But you can look at this one. So based on this, so this one is washed, this one is unwashed. And then we looked at, pH variations are not significant, in these situations. And whereas, this oxidation reduction potential, you can see, the flushed water from the biochar had reducing conditions. And for oxidizing conditions, for a washed biochar, you see the oxidizing conditions. So the fines are making the difference. So That's one of the things that we wanted to do, was we wanted to create a consistent filter material. So having fines in it, creates uncertain conditions as the flushing takes place. So the types of fines are making some difference in this case. Here are the results with electrical conductivity and total suspended solids. So we could see some measured electrical conductivity in this thing, showing that some ionic species have eluted through this system. In this case, this total dissolved solids is one of the important considerations for stormwater. For unwashed biochar, so we had a synthetic stormwater, we had this much of total suspended solids. Initially when we just added first to water, there was some suspended solids coming out of the biochar. That was the concern. That's why we wanted to wash it, because we don't want like a suspended solids released from the biochar, which becomes unacceptable. Whereas when you wash it, so synthetic stormwater had this much. But initially we wash with water. After washing the biochar, obviously you expect nothing, and then this concentration has decreased, as you see here. So basically TSS has been removed. These are the results for nutrients. Here I show the results of nitrate and phosphate. This is what is in the initial synthetic stormwater, and when we flushed initially with water, you can see there's not much coming out. And when we flush this much with the concentration, so it reduced to this, and basically it shows what is the concentration initially in the stormwater, how much is eluted in the effluent. So this is for unwashed, and these are for washed. So we did washed ones with a little bit more systematic. This is a synthetic stormwater, initial wash, 1 pore volume, 2nd pore volume, 3rd pore volume, and the final wash. So these results show that we were able to reduce the nitrate and phosphate to certain levels through this biochar. So those are the results. So heavy metals, again, we looked at. This is for unwashed biochar. But there are a lot of results here. So basically, this is all synthetic stormwater concentrations. Initially, what we had. When we flushed with water, there's nothing comes out, and with after flushing, you can see the concentrations of all the metals have decreased somewhat. I want to mention that we also tested other different filter materials, and in those filter materials, for example, some of them actually did not detect anything. So there are some other materials that are more effective than biochar. So just wanted to mention that. But biochar is reasonably effective in reducing the concentrations, but there could be other materials that can completely, remove this contamination. So again, this, washed biochar, I'm giving some data here. It's not about looking at the percentages. You have to look at the concentrations, because, the concentrations are the thresholds for discharge. Okay. So I have given the concentrations here for cadmium. Washed biochar in this one. What are the results for chromium? Here is the copper. So initially we had 4.63 and reduced to 2 milligrams per liter. Here is the lead. Because of the high pH, we haven't really seen much lead, eluted through the effluent. So nickel is the one contaminant that we found had a low removal compared to all the other metals. And we did also large-scale testing, and we found out that, for some reason that's not retarded in the material. This is for the zinc. Again, the concentrations, how much is the initial, how much is the final here. So you have the data. So this is about PAHs. We had the 3 types of PAHs in the synthetic stormwater: naphthalene, phenanthrene, and benzo pyrene. So these are the initial concentrations. And as I said, we always wanted to flush with the water, see if there is any PAHs in that. So there is nothing in there. And when we flush this one, these are the concentrations that we got at the end. So no PAHs were detected in this. And then in this naphthalene concentration reduced from here to here. And here is the phenanthrene. From here, it's almost to non-detectable levels. And at the end, benzo removal was not that significant. So overall, we had removal of substantial PAHs, but the removal of individual PAHs differs quite a bit. These are the results for E. coli. That's the main concern. We spiked the synthetic stormwater to up to these high levels, and after flushing it, after one pore volume, after second pore volume, after third pore volume, you see the concentrations in this one. It reduced it, but not significantly to the levels that we find, say, this material is very effective. So it did reduce. But then, at the final wash, there was some E. coli that was, able to elute. So overall, with these experiments, what we found is TSS removal is 86%, nitrate and phosphate removal were 86 and 47%. Compared to the initial concentrations that we chose. I must mention that the initial concentrations that we used were way high. I mean, those are the worst case conditions. You will never see that concentrations in any typical situation, but we wanted to create the worst case scenario in the lab. Here are the heavy metal concentrations, the percentage how much they decreased. Overall, as I said, 68% percentage reduction in PAHs, but individually they differed. Percentages differed quite a bit. So biochar was not really very effective in removing the E. coli. It reduced by 27%, but it was 27%. So overall, we could see the trend of decrease of contaminants using the biochar as a filter media. But we need more research on maybe selecting a suitable biochar, based on the feedstock, based on the production processes, that can be very effective to remove all the contamination, more than what I have shown here. So this is the project that's funded by US EPA. As I said, this is to build the in-ground reactive filter system. And, I have this paper published recently. You can download this one to get more details about this one. I also want to say that, as I said, biochar is one of the filter materials that we tested. We tested different types of filter materials, and we came up with a material that can remove all these contaminations to the threshold levels we want. The material is, no one material was able to take out all the contaminants. We found a combination of zeolites, iron filings, calcite, and sand. So there's a combination of these materials in certain proportion. We found that those are very effective. That mix of the materials is very effective to remove all the contaminant concentrations that I mentioned here. And we are in the actual process of, building one test plot at one of the beach sites and testing it out in the field. And we will monitor it and see how the performance, occurs. But unfortunately, the biochar was not included in the final design because of the reductions not reaching to the levels that we want. But I'm optimistic that one day, we can develop a biochar that can really do a better job than the biochar that we used here. Thank you.